So next, I want to introduce about the interrupts. Interrupts, as we mentioned earlier, are supported by using dedicated hardware. And this hardware is built into the microcontroller. They will respond to events from outside the microcontroller or microprocessor. The outside events will alert the processor that input is ready, or some other functionalities is ready or has to be taken care of. Really, the information or the meaning of the interrupt depends on who generates the interrupt. It will go through several steps internally when the processor responds to such events. The processor will suspend what it's currently doing. It will invoke its corresponding interrupt service routine. And then the interrupt service routine will do the things it's supposed to do, and most of the time it will interact with the application. So this diagram illustrates what the interrupt service routine is doing and how it interacts with the main application. Interrupt service routine, or ISR, is a very short subroutine that handles the interrupt. Now, short is kind of a vague description, but it should not take extended long time or waiting on other things that may not happen. We expect the interrupt service routine to be completed as soon as possible and dedicatedly for that particular interrupt. So what we see here is basically two things are happening at the same time, concurrently or logically. We have the processor doing some setup code for its main application. Let's say set up the GPIO registers to turn on and off the LEDs, or things that your main applications is supposed to do. Then it will also register the interrupt service routine. Now this step will differ from microcontroller to microcontroller. Depends on how the processor architecture is designed. You may be using different ways to do that, but you should basically use this at this step to let the microprocessor or microcontroller know this is your interrupt service routine for this particular interrupt. Some microprocessors may have multiple interrupts, so it's even more important that you register the correct interrupt for that interrupt service routine. If a microcontroller has only one interrupt, and then chances are you don't have to differentiate, so that's the only interrupt service routine you may have for this particular microcontroller. So register the interrupt service routine is important. That's the first step you have to do to ensure your interrupt is going to be handled by the correct ISR. Once you do that, then you can proceed on your normal task. Your main application will be here, and the processor will execute your main application or task code continuously. Because we're talking about embedded applications, so you will expect to have a if-and-then loop such that your main task will be executed all the time without stopping. But while you are doing that, this interrupt service routine has to be in place somewhere in your program segments, in your program memory. It may not be activated until you really see or receive an interrupt from the outside world. And that's this lightning strike refers to. This lightning strike is a indication of an external event that the processor has to respond. It may be saying from the UART, a new byte is ready for you to read, or this could be a warning signal from your temperature sensor where it indicates or some your other device which sense the temperature sees a warning sign. Say your current temperature exceeds the threshold, so it's beyond the safety requirement or the threshold, and that's a dangerous signal. So that could be another type of interrupt. So this interrupt could be different from case to case. And electrically, the interrupt could be level-based or could be trigger-based. So you could raise the voltage level too high or too low, or generate a pulse. Both are possible. So, but regardless, once this happens, the processor will do so-called context switch. So it will finish the very last instruction if the processor is still executing that instruction, and then it will start the context switch. By that we mean this processor will set its program counter to this ISR, the entry point, and then the next instruction will be the first instruction from this ISR. So this ISR, whatever program, whatever instructions you put into the ISR will be executed. You can have a certain program logic within ISR, but you should not have a very long subroutine that will take extended time. And the main purpose of this ISR is to respond to this interrupt. Again, it's the actual operation will be certainly different from case to case, but the main purpose is to deal with that interrupt. Once the ISR is completed, it will return to the main program. So it will resume to the main application, and the processor will continue from whatever instruction that it left out before the context switch. Okay, so this diagram on the top here shows the addresses for ATmega 168. The first column is the address, and you can see that these addresses all corresponding to one jump instruction. For this particular microcontroller, these addresses are fixed for these interrupts. So if there's a reset, this jump instruction will take the microcontroller to the function called reset. And for the second one, address 2, you'll take that to RQ0 handler. So these will be the kind of the entry point to these ISR routines. And these are the program addresses, not data memory addresses. As these low-end microcontrollers, they always have separate program memory from the data memory, and that's called the Harvard architecture. For modern microprocessors like Intel microprocessor, they have the same address space, but for these low-end microcontrollers, they always have separate program memory and data memory. So the triggers could be a level change on the interrupt pin to indicate that interrupt happens. You need to, you can also use software interrupt. So those interrupts are not really a external signal connected or sent to a interrupt pin. These software interrupt will be triggered when you execute a special instruction and write to a special register. The response from the microprocessor will be disabling the interrupt so the ISR can be entered safely. It will push the current program counter onto the stack. This is important. The current program counter really points to the next instruction in the main program. By pushing the current program counter onto the stack, the microprocessor will be able to get back to where it's being interrupted. So we can resume the execution of the main program. And then the next step is to execute the instruction at a designated address. And that's in fact the entry point, or the first, the address of the first instruction in the SR. We should do a few things in ISR. We should save and restore any registers it uses, because when you get back, you want to be able to restore the original values of the registers. It's similar, you do a function call. If you took microprocessor 1 class, you know the call conventions. When you have a C program, you call a subroutine or subfunction. The first few instructions will be those, pushing the registers into the stack to save the value. And once the subroutine finishes, then pop them back to the register. So we should do the same thing in the ISR to save any values that you may corrupt during the execution. Also, at the end, we will re-enable the interrupts before returning from the ISR. Again, this is an example of Berkeley Microblaze. What we show here is the memory map. So we have a 32-bit address. So it's a very large range. Some of them are unmapped. Some of them are really the real memory, like in this range from 4F to FFF. On the very top, this is the interrupt and exception handling table. Really, these places, these addresses like 0, 8, 10, 18, 20, and these several ones, these are hardware specific addresses. So what this means is that when this microcontroller gets a reset, so you will be, power recycle, or you'll be starting from scratch. What is the first instruction this microcontroller will execute? It will find its instruction from this address. That's why we say this is start and reset. This will be the address that the microcontroller will find its instruction. And this _star is the software label that you can use to refer to that instruction, to the address of the instruction. And we have interrupt handler, which is at address 10 in hexadecimal. So that's address 16. So also part of this region here. So that is the address where the microprocessor will find its first instruction. And that instruction can take you to other places using a jump. So you can see this whole memory region from 0 to all the way 8Fs. They are segmented into several subregions, and that's how they do this memory mapping. From using the color, you can easily see this region is mapped for real memory, so you can store data and read data from this region. If you want to operate on UR microcontrollers, you will find these controller and its internal control registers using this memory range. So from 840000 to FFF. So this range is where you can find the UR controllers. Timer registers are mapped in this region, and you can find other resources, interrupt controller in this region here. Again, this is just an example that's included in this set of slides. When we talk about the Atmega 2560 microcontroller after midterm, we'll know more. We're going to look at probably this slide and maybe similar slides again to see how its memory are mapped, if there's memory mapping, and how we're going to access these controllers, these individual resources. So don't be puzzled or confused by this memory mapping. Here I just want to use as an example to show you what we mean by memory map, and how we can possibly find these different resources. I noticed there's another question. Let me check that. Okay, so why is there unmapped area? Very good question. So we have such a large memory space. If you use the 64-bit, you can probably figure out it's, I think, 32 gigabytes of memory space. Do you think that you will be able to find a, 32 gigabyte of memory chip for a embedded microcontroller, which has only a few things to do? The answer is probably no. So even though we have such a large memory space, we do not have to use all the memory spaces, memory areas. And these areas, these numbers, is not something that we assign. This is mapped by the microcontroller by design. Now you may ask, why they do that. Very good question. I don't think I have a good answer, but you will find such cases that you won't be able to fill your resources to the whole memory region because you have such a large memory region. These unmapped area only means that they choose to map certain resources at different places. One reason that I can guess is these memory bits. So you can these bits will be different. So let's say this upper bits all 40. This is A1, A0. So these particular bits, I think bit 31, 32, bit 30 is a 1, and this these individual bits happen to be 1s, and that's how they get this particular address. It's really not that important because, as we explained earlier, these addresses are oftentimes hidden in the microprocessor's resource or header files. So a register, if it is allocated in this memory region, you will oftentimes find the name of the register is mapped to a particular address. So to you, it's really not a big deal where exactly they are mapped, as long as you have a way to refer to them. We're gonna see the actual code in probably 10 minutes. Okay, one more slide about Microblaze. Again, don't take this as something that you have to remember. This is just saying that this particular microcontroller supports one external interrupt source. So you can imagine that physically, this microcontroller has one pin that can be used to send interrupt signal into this microcontroller. And this pin is connected to the interrupt input port. The processor only reacts to interrupts if the interrupt enable bit in the machine's status register is set to 1. So this interrupt enable bit in this MSR is set 1. This is often the case for many microcontrollers. Although the exact control register's name is going to be different, you may call it differently, but there's always some bit in that register is called interrupt enable. Interrupt enable, you can think about this as like a master control bit. If you set this to 1, the interrupt is going to turn on. So the microprocessor will be able to respond. Doesn't mean that it doesn't. So when you have the interrupt enable pin is set to 1, does not mean you currently has an interrupt pending. It just enables the function, enables the interrupt function, so that your interrupt service routine is able to be triggered. On an interrupt, the instruction in the execution stage completes while the instruction in the decode stage is replaced by a branch to the interrupt vector. So this is really some details internally when the processor core is executing instructions. it goes through several stages: instruction fetch, decode, execution, and sometimes write back. So this is really give you some details about what exactly happening when the microprocessor is executing another instruction at the same time the interrupt happens. The interrupt return address is automatically loaded. So that is basically the next instruction the microprocessor was planned to execute if there were no interrupt. Now we have an interrupt, so that instruction, the addresses of that next instruction will be saved, so that later on when the ISR finishes, the processor can get back. In addition, the processor also disables future interrupt by clearing the interrupt enable bit in a MSR. So it's done by the microprocessor automatically. The IE bit is automatically set again when executing the interrupt return instruction. This is a quote from one of the pioneers in computer science, computer design, Dijkstra. This is from the article "The Humble Programmer." He wrote that basically saying interrupts are evil. In one or two respects, modern machinery is basically more difficult to handle than old machinery. Firstly, we have got the interrupts occurring at unpredictable and irreproducible moments. I think those are the two key words you may want to remember if you want to remember something from the slide. This is really saying that the interrupts are asynchronous. You don't know when they're going to happen, and you oftentimes cannot reproduce. And compared with the old sequential machine that pretended to be a fully deterministic automaton, this has been a drastic change. And many system programmers' gray hair bears witness to the fact that we should not talk lightly about logical problems created by that feature. So, of course, interrupts is not the end of the world. It's actually the beginning of a new world. But the fact is, you will have to deal with these unpredictable, irreproducible moments. The program design is more complex. People have to think more carefully about how they deal with such concurrent events. And we're going to be talking about these concepts with examples in more detail. Hope you guys are still energetic. Okay, so let's talk about one example of interrupts. Timed interrupt or timer. So what we see here is a typical way to use a timer or time the interrupt. On the left side, you see that the procedures for the processor to set up such a timer interrupt. You'll first do its usual setup work, enable, for example, the interrupt enable bit or other things. And then the next immediate thing the processor needs to do is to register interrupt service routine. And this interrupt service routine, as in our example, is for the timer interrupt. So whatever we want to do when the timer expires, and that should be put into this interrupt service routine, which is typically defined in a separate function. Here we just use statements, programs to register that ISR to this particular timer. Then we will initialize the timer. Initialize the timer can be a few steps. We can see from an example shortly. But initially, we will have to decide what will be the initial values of the timer, how long the timer will expire, things like that. So the timer is a hardware unit, a hardware controller within the microcontroller. So you will work with the timer unit through registers. As you work with many other components within the processor, you always use registers to do that. So it's important to understand what registers are involved and then be able to work with those registers accordingly. And the next thing is to, for the main purpose, for the main task, the next thing the microprocessor is supposed to do is to execute the task code. So that this is the main function you are operating. On the right side, what you see here, this is, you can think about this is the hardware timer unit, which will be counting the time ticks based on how long your time, the time elapsed of your timer that you configured here. When timer expires, this interrupt will be triggered. Like any external interrupt, this timer interrupt is often the time internal, but this is treated as the same way as the external interrupts. It will cause the normal execution of the main application to suspend. The microprocessor will jump to the interrupt service routine, which you register here at the beginning. And then in that interrupt service routine, you will do some updates, typically a counter. So you update your ticks, your sample, whatever variable that you want to record, the times or number of, or anything you want to do in ISR will be done here. And of course, it's going to finish at some point, and then that will let the processor resume the execution of the main task. What it doesn't show here in this diagram is the interaction in terms of the shared variables between this ISR and the main function, which, in fact, you will see more clearly through the examples in later slides. The ISR will also be responsible for reset the timer, so that the timer will redo the counting down or counting up, and then so that the next time expires, it can interrupt the processor again. So the reason we have different colors is because this timer unit is really a hardware-based. You are not writing code to update the counters in the timer. This is done by hardware internally as a part of the microcontroller. This is the software code you will write as the ISR for the timer interrupt. Let's use this microcontroller ATmega168 to show you how we can set up a timer to trigger interrupt every 1 millisecond. So we'll first look at some of the registers we'll use in this procedure. This TCCR is the timer counter control register. This one is, you will find such a control register for any timer in any processor. You will find something like this, although the name could be different. This control register is typically used to set up the mode of the counter, enable the interrupts, all these sort of control operations. This OCR is the output compare register, and this is really set the values of the timer in the sense that, how long the timer are going to expire after it resets. So this value is programmable and often is based on some calculation. If you want to have a timer, say in our case, 1 millisecond, using the frequency of the processor, you'll be able to figure out that, and we'll show you how we do that calculation. Timer interrupt mask is another control register you can use to enable or disable the interrupts for timer particularly. We're going to be using a term called prescaler value. You will see how we use that. But essentially, this is the value to divide the system clock so that we can use some much slower clock to drive the timer. On the left side, you will see some descriptions for this process. We assume the processor runs at 18.432 megahertz. And we will use the timer unit. What we want to do first is to set up an interrupt that will occur every millisecond. To do that, we will be able to generate a timer interrupt at every millisecond. Once everything is set up, then our ISR can be executed. But let's see how we can make that happen by leveraging the timer unit in this microcontroller. We will enable and set up this timer interrupt using the following code. We have 4 lines here, and each line is to assign a value to a particular register. This is TCCR1A, TCCR1B are part of the timer counter control register. You will see these names differ from microcontroller to microcontroller, but you will always find something similar. The first 2 lines of the code will put the timer in a mode that it will generate interrupts and reset the counter when the value reaches the value of OCR1A. So these 2 values, what matters really the particular bit in this value and also the particular bit or bits in this value. Because these registers, each bit will mean different things. So when we assign these values to these control registers, they will set or reset some of the bits. You can look into more detail looking at the data sheet to find out what are the bits in this register. But overall, these 2 lines are helping us to set the timer so that it will generate interrupt and reset the value using this value every time when the timer expires. Also, as a part of the control register, we set the prescaler value of 256. Interestingly, you don't see the 256, the value show up as the value here, because as we said earlier, the bit in this register really give you that value or even a different value if you choose to. This prescaler value means that the timer will run at 1/256th speed of the processor. So the timer will generate ticks at really 18.432 megahertz divided by 256. This will be the value that you get from this division will be the frequency of the time ticks of that timer. And the third line here is 71. This is the reset value, or you can think about this as the initial value of the timer. This value will be counting down every tick, and once it reaches to 0, an interrupt generates. So what we are doing here is to find out the value that we want to assign to this initial value or reset value of the counter. We will use this formula. We'll use the processor's frequency divided by the prescaler value, which times the interrupt frequency. So this 256 times 1,000, because this 1,000 microsecond, because the first value is in megahertz. So we convert that to microsecond. And then use that value, subtract 1, because we count from 0. So the final result is 71. So the 71 should be the value as the initial value or the value that has to be reset to the counter when the timer expires. Finally, we use this last line to enable the timer interrupt. Okay. So with these 4 lines, we are able to set up the 1 millisecond interrupt such that we will, the microprocessor will receive the interrupt every 1 millisecond. So if next we can, tell the microprocessor that the interrupt service routine, the particular interrupt service routine associated with this interrupt, then we're all set. Then we will achieve our goal of using that timer to do something every millisecond. So I want to stop here for a moment for you to think about the way you design your first lab. I didn't talk about timer interrupt for the Arduino. I do not require you to use timer interrupt for the first lab. But at this point, you should realize it's possible to use a timer interrupt for the first lab to count the number of seconds remaining for a particular light, for the particular color of the light. You can look up some of the online materials to find out how you set up timer interrupts for Arduino. But as I mentioned, you're not required to use that. It's fine if you use the delay function to count time and counting down. But there are options. Okay, back to this processor here. We're seeing on the left side a few lines of C code. These few lines essentially translates what we just described from the previous slide into program segments. In the main function, we assign these values to these 4 registers, and we explain what these registers are. But really, when you use this TCCR1A or TCCR1B and other registers, the reason you can use them is because these registers are defined in this AVR/IO.H. When you have a SDK from a microprocessor vendor, you will have example code like this. If it is in C, it will include any header files. And you will find out such similar lines like these ones that use register names as the variables and you can refer to. These names, definitely they are defined in one of these one of these header files. Let me see another question. Is 71 decimal or hexadecimal? It's decimal. So these are defined because these registers are memory mapped. But how, exactly where is this register? How are we able to access these registers? The question is, is valid because we show. We didn't show header file. We just show here, use the register name. But we'll see shortly how these register names are translated into actual code at low level for C compilers to properly handle these addresses. On the right side, I don't want to go into details. These are the logical functional diagrams for this timer. It has few registers that you can see, TCCR, NA, RNB, N refers to the number for the timer controllers. The microprocessor or microcontroller may have multiple timers. So you find, for this example, TCCR1A, and if you use a different timer, that would be TCCR2A. Likewise, OCR1B or OCR1, OCR2B, etc. Also, this diagram shows how the prescaler value are factored into the control logic of the timer. Like here, from the prescaler, will basically scale down the system clock and generate another internal clock for driving the counters down. Okay, now we have a few more lines of code. Hopefully, these code will explain how we go from the register names to the actual code. So what you see here, a few things. This is the initialize. You can think about this as the part of the main function. You also find these 4 lines that we referred to earlier. It's a little bit different from the previous implementation, the previous slide, where you see, you don't see these ones, underscore BV, underscore BV. Let me start from here. So yeah, so when you refer to TCCR1A, we can see this is another header file defines exactly what is TCCR1A. This is in IOMX8.h. Again, these names, file names are not important, but this definition line define this is the in C syntax. This defines a symbol, and it's coming from another symbol, underscore SFR mem8. SFR stands for Special Function Register, mem8, so it's an 8-bit register mapped in a memory address. The parameter here to this macro, another macro, is 0x80. Okay. Now if we go further on the chain, so underscore SFR underscore mem8, that is defined here. And it will take one argument as the memory address, and this is in fact underscore memory map IO byte wide data, and that's the memory address. If you look into further, that's defined as this. So eventually, when you use TCCR1A, this left part of the assignment statement is going to be recognized as this. Okay, so what is this? If you're familiar with the C syntax, this is really to say we want to use this value here, mem underscore addr, as the address. This address points to a location that stores the 8-bit value. And when we do the assignment, we essentially use this value to replace the value in that memory location. Okay, so that's how you essentially translate this register names to the actual memory mapped location. On the other hand, we have a few other functions. We have enable interrupt, disable interrupt. We have signal. That's the that's the interrupt service routine. Let me go through a few things that I just mentioned. Right. Yeah. So here is the interrupt service routine, and here's the delay in millisecond. This is part of the function you will call, and this here will be so this timer count will be decremented every time this timer interrupt happens. Okay, so this slide summarizes what I just explained earlier, how this line is going to be eventually translated into C code. So there's a few macro definitions, but essentially we're going to use this 80 as the memory map address so that we can refer to that control register for timer 1. So I spent quite some time to explain how this particular register is mapped or translated into this memory address. Really, this is specific to this AVR Atmel 160 microcontroller. You will certainly find different register names for the Atmel Mega 2560 that we use, or any other microcontrollers you may use. But the concept and the way these header files are defined are very similar. So I hope you can learn you've learned something from the first several slides, how these register names are eventually translated into the actual memory addresses. Any questions so far? Okay, so let's look at the next example. This is the Microblaze board that UC Berkeley used for their class. So they show the example how to set up a timer to trigger an interrupt every 1 millisecond. The code is in C, but it's very similar. So in the init function, you'll first set up the timer elapsed time. So how long is the timer going to expire? They call this function systic period set. This is the processor clock divided by 1000. That will give you the number of cycles per second. And we're using 1 millisecond, so we're going to be divided by 1000 to get the number of cycles per millisecond. That will take care of the initial values of the timers. And then we'll do tick enable to start the system tick counter. And then we enable the timer interrupt. So the timer will start working. And once the timer expires, it will generate interrupts. On the other hand, if we want to disable the timer, we'll just disable the system tick. Then we'll call this function and do the reverse. Okay, so let's hypothetically look at this example where you want to do something using timer, but you are not really doing the things that infinitely. In this example, what we want to achieve is to do something for 2 seconds and then stop. Okay, it's different from your traffic light controller. It could be different from many other applications where your task is going to be doing a particular thing endlessly in an infinite loop. But in this example, we're performing some function, some calculation, let's say, for 2 seconds and then stop. So how do we do that? As we see here, in the main program, we will first register a interrupt service routine. This interrupt service routine is going to be counting a timer count. And this is where it gets interesting. You can see this is the case I was talking about, where the ISR interact with the main function using a shared variable. So what is the shared variable here? Oh, I don't hear any volunteers.
Time count.
Yes, so timer count is the shared variable. And in the main function, we initialize the counter to be 2000. And we know earlier that the timer interrupt that we set up was for 1 millisecond. So our hope is, because the timer count is set up as 2000, and every 1 millisecond, this counter will be decremented by 1. Why is that? Well, because we register this ISR function here for this 1 millisecond timer interrupt. And because of the timer, 1 millisecond timer interrupt, this ISR, this function will be called once every 1 millisecond. And because our initial value is 2000, so we expect that this will be called at least 2000 times until this timer count value equals to 0. So if it's not 0, if this counter value is not to 0, meaning that we haven't really gone through the whole 2 seconds yet. So this part of the code will still run. This while loop still goes on until the timer count reaches to 0. Looks reasonable. So first of all, we notice here, in terms of this program segment, we have to declare this timer count. This is where we need to be careful. We need to declare this as a static variable. And it has to be declared outside the main function, because this variable should be accessible to both the ISR and the main function. When you put this declaration outside these function scopes, this will become a so-called global variable. So this will be allocated in the heap rather than the stack of these individual functions. So that's one thing. The second thing you notice here is we use a keyword, volatile. Volatile is a keyword in C to tell the compiler that this variable may change at any time and not entirely under the control of this program. Now, you may, I'm not sure about what this means, but this is important, especially when you have caches in microprocessors. Caches are small memory units that you will find in modern microprocessors. And these caches are used to store part of the data that you often use. You don't have to go to the main memory, and you can just load the value that you recently used from this cache, so you can speed up your program. They are useful, however, they are very sensitive to situations like this. If you have a value cached stored in the cache, then there's a risk that this ISR function or the main function will not see the real value due to the due to kind of the conflict that you will the updates will not be reflected right away to be visible to either of these functions. So volatile really tells the compiler that this value should not be cached in a way to they should be treated to effectively to immediately update it whenever this value is updated in memory. This ISR, as we explained earlier, this is a function. You will use this function, or you can use a different name. It doesn't have to be ISR literally. You can have other names, but you will have such a function. You have the operations defined in this function as the service, as the particular operations, and you register that to be your interrupt service routine. Once you register, then when interrupt indeed happens, this function will be called. Because earlier we set the system tick as 1 millisecond. So when this interrupt is enabled, this ISR will be called every 1 millisecond. So here we're going to talk about the important concept of concurrency. Concurrency refers to the fact that logically you have two parts of the code going on at the same time. One part is the main function. So this function is going to be executed, especially when you get to this while loop. So this while loop will go on for some time. But logically, you can view this ISR is also active, because from time to time, in fact, precisely every 1 millisecond, this ISR will be executed. So during the whole process, this ISR is not done. It has to be called again and again. Also, the main function, especially the while loop, is also being executed. So this is what we call concurrent code. They logically run at the same time. In this case, between any two machine instructions in the main, an interrupt can occur, and the upper code can execute. So concurrency is a good thing, but you will see right now there's things that you need to consider to be careful. The question you want to ask on this example is there an issue with this code?
You can't trigger any other interrupts?
Sorry, I couldn't hear your voice. It's very noisy background there. Can you speak up or say it again? Okay, any other volunteers? Okay, so the comment was you won't be able to use any other interrupts. That's a good point, but here we're not saying that. We didn't prevent the microprocessor to enable other interrupts if there are more than one interrupt. So what if the interrupt occurs twice during the execution of this code? Okay, considering of time, let me go on. So let's say if your timer at this point, when you execute this while loop, your timer count is 1. Okay, and when you check this condition, it's not equal to 0. Right? So we're going to be going into this, whatever code you have within the while loop, we're going to be executing this code. And we expect this code to go on for 2 seconds. So that's a long time. So you will likely to have this ISR, this routine to be called multiple times. Let's say this ISR is called twice. Now, when you enter this while loop, well, when you at this point, your timer count is 1, and then you have 2 interrupts, then your timer count, this value will be decrementing twice. So that'll become -1. And what is the problem with the -1? The problem being that when you have a -1 as the timer count, the next while loop is still not equal to 1. Sorry, it's still not equal to 0 because actually you bypass 0. So you never reach the true condition or false condition of this check. And your counter keeps decrementing, so you're going to be having a negative value, but you will never reach to this condition that ending this while loop. So we improved this example. We'll do some checking to see if the counter is 0 or not. Based on that, we'll decrement. You can take a look at this improved example. I see we're running out of time. I will have to probably end the lecture today. We only have a few slides left. I think we can quickly cover that in the next class.